Welcome back. My name is Dr. Elvis Asson. I am a senior climatologist at Climatologic Inc., an adjunct professor in the Global Institute for Water Security, University of Saskatchewan, and an associate of the Climate Risk Institute. Today, we will learn about observational data and considerations for use. This session is divided into three interconnected parts. In part 1, we will focus on what is historical climate data. In part 2, we will discuss how to use climate data to support adaptation. And in part 3, guidelines for the usage of historical climate data and limitations will be presented. What is historical climate data? An initial scoping of a climate risk assessment project will identify the climatic and hydrological variables of interest to a project. These are typically variables that guide engineering design and variables associated with hazards to a project, such as peak flood discharge. An important aspect of a climate risk assessment will then be the interpretation of these changes in primary meteorological and hydrological variables with respect to more complex phenomena such as floods, droughts, and changes in watershed conditions and hydrology. In the context of a climate risk assessment, historical climate data comprise of observations and climate model simulations. For example, in this figure, the black bow line represents climate observations up to the period 2020, while the gray small lines represent historical simulations from climate model outputs. So it is important to distinguish this. When we talk about historical climate data, we are actually talking about observations as well as climate model output during the historical period. It is important to understand that our climate system, when using on observations for climate risk assessments, that the climate is not constant. While the weather varies daily, climate captures variations on all time scales from one decade or century to the next, and even on a seasonal and yearly basis. For example, some seasons are warmer than others, and annual precipitation is greater in some years than in others. These differences are referred to as natural variability in climate or simply climate variability. On the other hand, climate change is a long-term continuous change, an increasing or a decreasing trend. The change is strongly modulated by the natural variability in the climate. For example, this figure shows annual mean temperature data plotted over time. Clearly, the annual temperature is not constant. It varies from year to year. This natural variability will always persist, even if the long-term trend is for annual temperature to increase. What does this mean? This implies that to pick up a clear climate change signal, observed historical climate data must be averaged over a relatively long period of time in order to be used in the climate risk assessment. This is often based on what we call climate normals. For example, a 10-year average could easily be influenced by a short-term warming or cooling trend, whereas a 30-year average would likely smooth out much of this effect. So for climate risk assessment, we are saying that it is important for us to average data over a long period of time, typically 30 years, instead of just using decadal data sets which could be influenced by internal climate variability or natural climate variability. Some of the key types of observational climate data set will now be discussed. Appropriate observed data and information are critical for climate risk assessment. So the key types of data that are typically required for infrastructure climate risk assessment include station data, grid meteorological data sets, grid analysis data sets, and remotely sensed quantitative radar data sets. And the key historical variables that we require can be classified as meteorological, hydrological, and other environmental variables. We'll dive into each of these categories subsequently. Key relevant meteorological variables that we typically use for infrastructure risk assessment are temperature, precipitation, humidity, wind speed, direction, radiation, and other variables which are project specific. In terms of hydrological variables, we typically require runoff volume, discharge depth and velocity, groundwater storage, soil moisture, water temperature, water quality parameters, and others. And in terms of environmental variables, we typically require sea level rise amongst others, and these are project specific. So for some projects, we will require most of these variables, most of all of the variables, but in some other projects, we require just a few of the variables such as precipitation and temperature. So the location of the project matters, and the time scale of the project also matters. Now, how do we use historical climate data to support climate risk assessment? The usage of historical climate data to support climate risk assessment depends heavily on the impact assessment approach we adopt. Typically, assessment approaches are classified into top-down and bottom-up approaches. Top-down approaches emphasize understanding the plausible impacts by representing different sources of uncertainty. And typically, this approach results in what we call a cascade of uncertainty. For example, it starts with a representation of different climate scenarios, global climate model simulations, a possible downscaling step, and assessing the range in outputs from a particular climate model. For this kind of approach, long-term data greater than 30 years, either station, graded, or reanalysis data sets are required. The other approach is a bottom-up approach, which starts with an attempt to identify the nature of climate risks, such as floods, droughts, and heat waves that a system is exposed to under past and current climate. Under these circumstances, for the bottom-up approach, real-time station data, satellite data, and radar estimates are very important for stress testing the system or doing a sensitivity analysis of water infrastructure to climate change. So station data versus graded data. The usage of station versus graded data depends on the scale of analysis. For example, for a spatial climate risk assessment involving accounting for joint adaptive capacity across locations, we will typically require graded data sets such as reanalysis, satellite, and radar estimates. While for a site or point climate risk assessment, we will typically require station data for those kind of assessments. The temporal resolution is also very important, and this will depend on the level, that is the detail of the climate risk assessment. For a very high level climate risk assessment, seasonal and annual summaries of hydrometeorological variables may suffice. Whereas for detailed climate risk assessments, down to sub-daily and daily sequences of meteorological and hydrological variables may be required. It is important to understand how to extract data at engaged locations. Use of station data that is climatologically similar to your project site is recommended. Test for climatological similarity and use data from a nearby station if your project site does not have a weather station. You can also apply regionalization techniques to determine station similarity. In the absence of station data, make use of graded data. And to make use of graded data for your project site, extract data from the project location using one grid or 4 surrounding grids. Variables such as precipitation will typically require averaging over multiple grids to reduce the impact of smoothing, which occurs during interpolation of station data to produce graded data sets. Example uses of climate data for risk assessment. For a very detailed climate risk assessment, for example, design of new climate resilient infrastructure, will typically require 30 years of precipitation data analyzed for specific sites and locations. For moderate assessments, such as risk assessment of all dams in a given region, will typically require threshold data, for example, number of days exceeding 35 degrees Celsius. Characterizing historical climate data and impacts is important. Typically, we will ask what impacts have already occurred. Start by obtaining observed historical climate data at a local climate station and analyzing average conditions and trends. Then compile anecdotal evidence based on local observations. We also used observed historical data to develop application-ready climate projections. So historical climate projections are biased when compared against observations, and we typically apply a post-processing step known as bias correction to produce application-ready data. So on the top panel here, you can see the observations, the black line, is far below what the climate model gives us during the historical period. So we typically apply a bias correction technique to move the climate model output closer to the observations. So this is where observations connect with climate model simulations when doing climate risk assessments and developing application-ready data to support those assessments. So in part 3 here, we'll look at some of the guidelines and limitations for using historical climate data. It is common that the density, the distribution, and record lengths of weather and climate observation network varies considerably within the Nile Basin, just like many other regions in the world. And these can often result in challenges when working with climate data, especially when we want to calculate climate normals, identify long-term changes, and gathering information on extremes to support our climate risk assessment. This is critical. The density and distribution of monitoring networks and stations has been declining significantly over time in the Nile Basin. For example, in Uganda, the number of meteorological stations started increasing in 1952 up to 1980, but then towards 2012, the density dipped down to close to 1952 levels. Same in Burundi, the density of stations has been declining over time. Because of the limitations in climate observation stations, such as rain gauges, in recent years, satellite data products have emerged to fill some of the gaps left behind by gauge stations. For example, this we have the GPM, that is the Global Precipitation Measurement Nation, and we have the Tropical Rainfall Measurement Nation. These are all satellite-based data sets which provide graded, consistent data sets across many regions. So they vary, the region of coverage varies. For example, TRIM covers the tropics only, while the GPM covers mostly regions between 60 degrees south to 60 degrees north. There are many data sources, global data sources, which we can use to do climate risk assessments in the Nile Basin. One example is the USA data portal and the Climate Hazard Center at University of California, Santa Barbara has produced this very nice station data set called CHIPS, which is global and can be used for climate risk assessments. It is also important that when doing this risk assessment, we should incorporate traditional and local knowledge. Traditional and local knowledge can provide invaluable insights into long-term local and regional climate, and becomes particularly important in locations with limited instrumental records. And this is key when doing a climate risk assessment and adopting the bottom-up approach to do stress testing of the system. This is where traditional knowledge becomes key. To conclude, overall guidance for using historical climate data sets for infrastructure risk assessment. 1. There are many sources of climate data and information available. 2. Understand climate data limitations and considerations. 3. Always consult a qualified, experienced climate expert to source the right data for you and analyze quality of the data, homogeneity of the data, especially for station observations. Station observations typically have a lot of gaps, and using this data will require that you consult a qualified expert to make sure the data used is homogeneous and representative of the project site under consideration. With that, I will say thank you for your attention.